Hi, today we're going to continue talking about bonding, but definitely going to be a gear shift from the ionic model. So, something I wanted to get into a little bit was an idea that I introduced a little bit in talking about polyatomic ions, and maybe a question that you've been having for a little bit of time. What we have in the illustration on the left, the animated GIF, is that two dogs are playing tug of war, and we have a winner and a loser. And then what we have in the picture on the right is something that looks a lot closer to a tie. And if, like I said earlier, that we were going to compare electronegativity to pull on a pair of electrons between two atoms, a relative measure, A, it's possible to have two electrons be pulled between two atoms, and B, it's possible to have that pull be strong enough between the two atoms that there isn't a clear winner or loser. And while talking about dogs tugging on a rope doesn't really directly relate to chemicals, it actually works pretty well for what I'm trying to get at. This is fluorine, the element. I have on the left a picture of the MSDS, which is Materials Safety Data Sheet. This is a document that needs to be on hand anywhere chemicals are stored or used. So you'll see them at places of work. Anyone on a custodial crew. We have an MSDS at school for every single chemical that we have in the building and that we use in our labs. And they're very rigidly put together with how they present their information and what kind of information they have to present. And I wanted to talk about fluorine because if you look, Matheson Trigas is kind enough to make theirs available on the internet. If you look, there's the information about the chemical, the company, and then a little bit about the hazard information. You can see it's a rating of 4 on both health and reactivity. 4 is the worst score. 0 is the safest. This stuff is nasty. But particularly, I wanted to talk about the physical and chemical properties because if you'll see, some information down here is kind of interesting, and I blew it up for us to talk about here. This 2 is supposed to be a subscript, so it's supposed to be F2. But it is a yellowish-green gas, pungent odor, sure. But it says molecular weight, 38. So first off, the word molecular is now being thrown about. And second off, we get 38, which ties up with 19 times 2. And so what this seems to suggest is that if you get a tank of fluorine, everyone kind of knows that it's listed in molecules and molecules that are pairing up your fluorines. So this should yield a number of questions. Basically, why and how do fluorines pair, right? We spent a long time talking about how fluorine has the highest electronegativity and what that means. I mean, when you get into an ionic bond with fluorine, fluorine always wins. It's a big negative. So how is it possible that these two fluorines are traveling in pairs? And to look at that, I kind of wanted to just work with you to draw the Lewis dot structure for fluorine. So forgive me for a second. I need to draw 2 fluorines. So remember that we were able to exercise some rotational freedom with respect to making your Lewis structures for fluorine, right? We have 7 valence electrons, so I showed 7, 3 pairs, 1 unpaired. But I wanted to make a small change here, and I wanted to orient them this way, because if you look at it, oh, wait, yeah, that's the right color. Actually, I want that one. If you had fluorine atoms just floating around, I mean, the MSDS said that isn't what happens. So I'm really trying to understand how we can show this. If you look at these 2 fluorines, all I did was rotate the one on the left. We have this region where it looks like things could fit together quite nicely. It's this area right here. If we were to bring these 2 fluorines together, the electrons would kind of just overlap. Now, obviously, a Lewis structure is not indicative of anything other than our own personal bookkeeping, but it does still fit together quite nice, like a little bit of a puzzle. And if you do roll back and you say, oh yes, let's not forget that these electrons exist in orbitals and each orbital can hold 2 electrons, and all those rules that dictate how electrons fill into those orbitals, you could say that this electron is unpaired in an orbital of fluorine and this electron is unpaired in an orbital of fluorine. And if it would be possible to put the two atoms together and have the unpaired electrons occupy the same orbital, that would work quite nicely. So let me redraw this with them a lot closer, and that shown. We're gonna make the one fluorine dots and the other one X's just to really delineate what's going on. So what we have like here is this would be our way of representing that on paper. I'm gonna clean that up the tiniest bit. This would be a shared pair where we've got electrons coming from two different atoms but occupying a space where two atoms can kind of lay claim to them. This is what we call a Lewis structure for a covalent compound. This is our introduction to covalent bonding, something you may have heard before, so I'm going to just get through a little bit of background information. And while I do want to recopy the fluorine Lewis dot structure that I just drew. So in the case of nonmetals, you have a situation where two atoms are simultaneously being in the position of being unstable because their electron configuration does not match a noble gas, but also not really being in a really good position to have anything happen to fix that. If you have a tank and it's pure fluorine, these are all atoms that have supremely high ionization energy and electronegativity, so all these atoms would pull on electrons if electrons existed that could be pulled easily, but none can. So really, the best way to think about this is saying, well, this is a lot like a situation where both atoms are acting in such a way to say, well, it's kind of better, not that they have brains, but it's kind of better if we both share this pair because then we both kind of get what we're looking for. I know it would be nice if we could get our own electrons, but at least in this case, we can kind of behave a certain way. And our definition here is that the electrons are basically two nuclei pulling on one pair of electrons is our definition of covalent. Literally covalent, as in like shared valence. The shared electrons are found in between the two nuclei when we're drawing our Lewis structure. If we were to talk about like electron clouds, again, that cloud would reside in between the two nuclei. And for the Lewis structures, you can see that I've drawn a second structure here. You are allowed to draw a line instead of two dots, so you might see that. The line really represents the shared pair, but this represents two electrons, and this represents two electrons. One final word about how this works. I did mention this briefly, but I want to, take a little bit more time to really drive the message home. The whole goal behind covalent bonding is that when this takes place, this fluorine acts in such a way that those 8 electrons that are in this circle belong to the fluorine on the left, and then the fluorine on the right acts as in those 8 electrons are belonging to the fluorine on the right. And remember that we're only showing 7 electrons per fluorine, so if the fluorine is going to act stable when it has 8 electrons, F2 should have 16 electrons. But F2, for this dot structure only has 14 that it's dealing with. So like the bookkeeping behind this is covalent bonding is a model that allows these atoms to kind of make up that deficit of electrons, and they behave as if those electrons are allowed to be counted twice. Now this happens with more than just fluorine. Obviously any atom with a high electronegativity and a high ionization energy can display this behavior. Other atoms, other nonmetals, carbon, nitrogen, oxygen, chlorine, bromine, right? All of them will display this, but also hydrogen's a nonmetal, and I did want to take a second to talk about it, right? Because hydrogen's electron configuration is 1, and its nearest noble gas is helium, whose electron configuration is, 2. This means that when hydrogen gets involved in covalent bonding, it does not have this octet rule about it. It has more of a duet rule. Hydrogens only make one bond, and then they're kind of done. They don't have the propensity to get involved with pulling more electron pairs around them because, well, the nucleus is only one proton, so it doesn't really have the strength to pull that off, and the effective nuclear charge becomes negative on past the valence shell and all the stuff we've talked about before. So our rule is really like 8 in most cases, 2 if there's hydrogen, and that's why the rule gets a little bit flimsy and it's a little bit more of a model than a rule. It is worth talking about making a distinction, if anyone cares to count about these things, an unshared pair versus a shared pair, or a lone pair versus a shared pair. Lone pairs are electrons in a Lewis structure, covalent, that are associated with only one of the atoms present. So this would be a lone pair, LP, and this would be a shared pair, SP, here, between the two atoms. And so now it starts to matter where these electrons are located. When we had the atoms, we can rotate our electron pairs, but now it actually kind of matters, or at least you got to make sure you're drawing things appropriately. So just to be clear, if we had hydrogens only have 1 electron each, but we are in this position of saying a stability could be gained if these 2 hydrogens became H2, because each hydrogen would be able to act as if it had 2 valence electrons and then was isoelectronic with helium. Just a couple more ground rules. It has only been observed that each bond is only allowed to be 2 electrons at a time, and it's only between 2 atoms. Both of those probably have exceptions that you're going to see later on in future chemistry courses, and by probably I mean definitely. But for now, let's just start with the simple rules. A bond is 2 electrons between 2 atoms only, 1 bond at a time. It might be interesting to you. You might start to notice that, well, we talked about F2, and then now we have the H2, and we mentioned earlier this idea of a diatomic element, where it's only one type of matter, one element, but it is traveling in pairs. There are 7 elements on the periodic table that display this property of when they exist in the elemental state, they are paired up. So these diatomic elements. It spells out Brinkelhoff, which is how I remember it. There are 7 of them. It makes a 7 on the periodic table if you don't count hydrogen. There are a couple ways to remember it, but Brinkelhoff is the one that I latch on to. So that's all well and good for those 7 elements, but it's also possible for covalent bonding to exist between heteroatoms, atoms of different elements. As long as all the atoms involved are nonmetals with high electronegativities and high ionization energies, this will take place. So how you figure out what these structures look like, well, I'm going to go through a couple for you, but it might be good to stop on one new vocabulary word. The word molecule is synonymous with covalent. Well, not synonymous, but only associated with covalent. If you ever see the word molecule, you know that we're talking about a covalent substance. And if you are talking about a covalent substance, that's the only time you're allowed to use the word molecule. So don't call anything else a molecule. But it's a bunch of, as it says there, here are your rules for it. And the big thing is that it is discrete from other particles in the matter. I'll show you what I mean, though. Let's go through this process of drawing a Lewis structure for a covalent molecule. The way I do it, first, I'm going to draw all of the associated atoms with their elemental Lewis structures. So this is HCl, right? And you can see you've got 1 electron on the hydrogen and 7 valence electrons on the chlorine. If you need a reference table, there's a link above my head. And then I circle any unpaired electrons between 2 atoms to make a shared pair. After that, I take a look, does everyone have the right number of electrons? Well, the hydrogen now has 2 associated with it. The chlorine now has 8. Those are both good numbers for those elements. And then as a last step, I clean things up. I bring the atoms closer together. I might turn the dots into lines. I make sure I recopy everything with the right number of valence electrons. And that is the Lewis structure for hydrogen chloride, or HCl. We're not going to worry about naming today. When I say that that molecules are discrete, that means that if you had like a tank of HCl, all of the different particles of HCl would be separate from all the other particles. They might float around if it's a gas, or flow over each other if they're liquid, and even if they're a solid, they're getting close together. But there's a big difference between this H and this H, like this H is associated with this Cl, and that's it. They don't like trade around or anything. To draw the Lewis dot structure for CF4 is a little bit more involved. I'm going to draw all of the elements really quickly. That's a lot of dots. And then I want to go through and I want to make bonds. So the first thing you might notice is that I drew the carbon, not the way you're used to seeing it. I did unpair those first two electrons. I don't really want to get too much into it. I'm just going to say that when you're making molecules, there's basically such a thing as bonding carbon and non-bonding carbon. It gets into a whole thing called hybridization that I do not want to get into right now, but just so you know, it might be better to draw your carbons as having 4 different bonds. And this gets me to something I actually wrote. I wrote it right there. Right here. How many bonds can an atom make? There's a quick way to make this calculation, and it's to take 8 minus the number of valence electrons. So for carbon, 8 minus 4 is 4, makes 4 bonds. For fluorine, 8 minus 7 is 1, makes 1 bond. You can do the same thing for hydrogen and chlorine, as long as for hydrogen, you remember again, 8 is an 8, 8 is 2, and you still get 1 bond and 1 bond. Next, we're just going to start pairing them up to make these paired electrons. See, this is why I wanted to unpair the 2 on the carbon so that the carbon can actually make 4 bonds. This is a complete mess. So this is why I usually say come back at the end and you have to clean it up. So I'm going to do that. As a final note, it is kind of worth having the quick discussion of, when you have 5 atoms and you're trying to make a molecule, where do you put them, right? Which one goes in the middle? Usually, along with, being able to calculate how many bonds an atom can make, it might be worth trying to think about that. The element that goes in the center is almost always, you'll probably see an exception soon, almost always the lowest electronegativity. That ties into the whole needing to make more bonds, making more bonds because it has fewer valence electrons. It ties into that trend, but low electronegativity in the center is an easier thing to remember than trying to think about the whole process. I should note also, before I move on to 2 more examples, there is a way to check whether or not you've drawn a good structure. One of the things you can look at is, other than making sure every atom has an octet associated with it, or duet, is you can count up the total number of valence electrons that should be present versus how many are present. So as a quick math, plus 1. We've got 1 for hydrogen and 7 for chlorine. That's a total of 8. And in this structure, we have 8 electrons showing. So that's good. For this one, we have 4, and then we have 7 for each fluorine, and there are 4 of them, which comes out to be 32 electrons. And then if you counted this up, you'd get 32 electrons. It's a good thing to do at the end to make sure you're not forgetting any lone pairs, that you're not making too many or too few bonds. So 2 more examples before we finish up. Here they are. If you want to try and draw these by yourself, you are welcome to do so. Just go through the steps I just gave. You can pause the video if you want to do that. But I'll go through the steps with you, doing these really quickly. So step 1, we're going to draw all of our elements, and I'm going to try and do both at once for this. Okay, and then we start pairing up. So before I start pairing, though, this is why it's really, really important to make sure you are 100% confident with drawing Lewis structures for atoms, because nitrogen, if you don't have 3 unpaired atoms, it's going to look very confusing when you try and get everything bonded in. Remember, a covalent bond is when 2 atoms share a pair of electrons between them and only them. So we have to be making a pair between the electrons of nitrogen and the electrons of hydrogen to make it count as a bond. I'm going to connect them with a different color so it's a little bit, cleaner and has fewer loopies. Whatever you put in your notebook is good for you. So that would be like how we make our pair, right? You can't just draw a bunch of lines to the nitrogen spaces. You have to be sharing, if you want to bond between nitrogen and hydrogen, 1 electron from nitrogen and 1 from hydrogen. And then we're going to clean this up, and this is what ammonia's Lewis structure looks like. For this particle over here, it's called methanol, if you're curious. I could make bonds from each of the single electrons of carbon to the bonds of each of the hydrogens. But if I were to do that, I've completely forgotten about the oxygen. So sometimes you have to do a little bit of guessing and checking before you get too comfortable with it, until you get comfortable with it. And you have to try and constantly go back and say, am I addressing everything I need to? Am I connecting everything I can to make sure that each atom has a more stable configuration than being unbonded? And I think what you need to do here is actually make a bond to the oxygen, since the oxygen can make 2, right? 8 minus 6 is 2. And then this is what your structure will look like. So give me a second to clean this up. And here we have a Lewis structure for methanol. Again, it's really important to, remember you can rotate these lone pairs and bonded pairs how you need to, but it's really important to have your clear notation so that it does not look like there's a bond between those two hydrogens down there. The bonds from the hydrogens are up to the oxygen and the carbon. So to sum things up, covalent bonding exists. It's a thing. And this is one of the varied ways that elements interact to have a more stable electron configuration to match that nearest noble gas. It only is displayed between nonmetals with your high electronegativity and high ionization energy. There is a difference between a shared pair and a lone pair of electrons. You are still limiting yourself to 8 valence electrons around an atom. The number of bonds you're allowed to calculate, right? 8 minus the number of valence electrons as an atom. And then usually you're going to put those less electronegative atoms in the middle. Thanks for watching.